In this video, we are going to look at field extensions, but I encourage you before you watch the video to look in the problems in the PDF file called Introduction to Field Extensions. That'll give you an introduction to the type of issues that we're going to be dealing with in this video. Alright, so as I mentioned before, we're going to look at field extensions. We're going to first define what field extensions are. We're going to determine a field extension in a pretty simple example. And then we're going to show how to determine more complicated field extensions. Alright, so suppose you have fields E and F such that E is a subset of F. And we're going to make two definitions off of this relationship. First, we're going to say that E is a subfield of F, which hopefully is seems pretty familiar terminology looking back at the work we did with subrings. And then we say that F is a field extension of E. So what's happening here is we're looking at the same relationship between E and F, we're just looking at it from different perspectives. If we're looking at it as one field being a subset of the other, the subset is called a subfield. If we're thinking of one field as containing another, we call that a field extension of the other field. So just as a reminder about Q of square root of 3, that is the smallest ring that includes both Q and 3. And if you remember the work we did it with the integers, but it's very similar with rational numbers. Q of square root of 3 with the square brackets is equal to a plus b square root of 3, where a and b are rational numbers. So the question is the smallest ring that includes both Q and square root of 3 also a field? Well, let's see. And in particular, is it a field extension of Q? Because remember, if we let b equal 0, we can see that all the rational numbers are contained in Q of square root of 3. So most of the axioms for being a field are automatically satisfied by being a ring. The only additional requirements we have are it needs to be commutative, which is clear. Q of square root of 3 is contained in the real numbers, which is a commutative ring. So then all that leaves us is we have to show that every non-zero element has a multiplicative inverse. So here's our general strategy that we're going to eventually carry through to more complicated examples. So the first question we're going to ask is, when do we have a plus b square root of 3 equals 0? Now, it is certainly true that if we have a and b equal to 0, that will make it 0. But the question is, are there any others? And as you saw in the examples in the in-class activities, a and b being 0 is literally the only possibility for a plus b square root of 3 being 0. So now the question is, what if a plus b square root of 3 is not equal to 0? And what we'd like to find is a multiplicative inverse for it. And what that means from the first bullet point is that either a is non-zero or b is non-zero or both. And if we do have a non-zero, what can we multiply by a plus b square root of 3 to get? Well, we want to get 1, right? That will make it the multiplicative inverse. But let's not be so greedy. Let's have some lower, less ambitious goals and just get a rational number. Well, as you saw in the in-class activities, if you multiply it by what we used to call in our old algebra days the conjugate, a plus b square root of 3 times a minus b square root of 3 gives you a squared minus 3b squared. And you can see that that is a rational number. And not only that, but you prove that it's not equal to 0. Again, you have to do some work to prove that. Assume it is equal to 0, get a contradiction. But that's something that you can do. And so if we sort of divide both sides of that equation by a squared minus 3b squared, which we can do since it's non-zero, and then apply it only to the a minus b square root of 3, we see that the multiplicative inverse of a plus b square root of 3 is a over a squared minus 3b squared plus negative b over a squared minus 3b squared times square root of 3. Which tells us that every non-zero number has a multiplicative inverse that is in that same field, in that same ring. And that tells us that Q of square root of 3 is a field. So now we're going to try to apply the same strategy to a more complicated example. In this case, we're still starting off with the rational numbers, but now we're going to add a number alpha and look at all the numbers a plus b alpha, where a and b are rational numbers. But now alpha is going to be, well, it's going to be a root of the polynomial x squared minus x plus 1. In other words, alpha squared minus alpha plus 1 is equal to 0. It satisfies that equation. And if we wanted to solve for alpha squared in that equation, that tells us that alpha squared is equal to alpha minus 1. Both of those equations are equivalent. It just so happens that the second one is going to be a little bit more helpful to us somewhere down the line. So I want you to know that both of those equations work okay. Now, it turns out that alpha is not a real number, and if you don't believe me, you can check it yourself, actually. All you have to do is use the quadratic formula to solve for alpha, and you'll see that you get a non-zero imaginary part of that number. So it's going to be a complex number that is not real. So if we want to prove that Q of alpha is a field, which is what our goal is going to be, we would like to first prove that it is a ring. That is not going to be so bad. I'll let you check that. It is a subset of the complex numbers, so you should be able to use the subring test to check it. So we know it's commutative multiplication, so all we have to do now to prove that it's a field is show that every element has a multiplicative inverse. So we're going to start off the same way we started off before. First, we're going to determine when a plus b alpha is equal to 0. When a plus b alpha is not equal to 0, we want to find a multiplicative inverse, but we're first going to have a less ambitious goal. What do we multiply it by a number in Q of alpha that can give us a rational number? And that's going to be hard, but we're going to do it. And then you're going to use that number to help you find a multiplicative inverse for a plus b alpha, just like we did for a plus b square root of 3. All right, so first goal. Let's see if we can figure out when a plus b alpha equals 0. Now, certainly when a and b are both 0, that is going to be true. But the question is, are there any other a's and b's that can make that 0? Well, let's see. So there are two cases for b, right? Either b could be 0 itself, right? And maybe a isn't 0. Or it's possible that b is not equal to 0. So we're going to take those two cases separately. So if b is equal to 0, then life is pretty good, right? A plus b alpha is equal to 0. That's our assumption, right? B is 0, which means that b times alpha is 0. And that equation then becomes just plain old a equals 0. So when b equals 0, then a equals 0. That's the one that we were looking for anyway. Right? So we have a equals 0 and b equals 0. But what if b is not equal to 0? Well, if b is not equal to 0, then we can actually take that equation, a plus b alpha equals 0, and we can solve for alpha, right? Usually the thing that's stopping us from solving for alpha is we're not sure whether we can divide by b or not, right? If we can't divide by, if b is 0, we certainly can't divide by it, but we know b is not 0, so we can divide by b. Now, a and b are both rational numbers, and so when we divide them and take their multiplicative inverse, that's going to give us a rational number. But that tells us that alpha is a rational number. And not only is alpha not a rational number, it isn't even a real number. So that's a contradiction. And that means that we can't have b is not equal to 0. So the only case we have is when b is equal to 0. And if b is equal to 0, that means a is equal to 0 as well. So we've proven that the only way that a plus b alpha can equal 0 is if a equals 0 and b equals 0. There are no other ways. Not only does that work, there are no other ways that work either. So that's nice. So now we get to assume that a plus b alpha is not equal to 0. And remember, what that means from all the work we did in that previous slide is that either a is not 0, or b is not 0, or both. Right? We can't have them both be 0, but we can have anything else. So now what we're going to do is we're going to find a number in our field extension, in our ring extension Q of alpha, that we can multiply by a plus b alpha to get a rational number. And again, we don't care what rational number it is now. Most important, we care that it's a non-zero, but that's all we care about. So we have two cases, right? Again, if b is equal to 0 and b is not equal to 0. If b is equal to 0, it's actually going to be pretty easy. If I want to find a plus b alpha, the multiplicative inverse, b is 0, so that's just a to the negative 1. If a plus b alpha is a non-zero number, that means since b is 0, that means a is not equal to 0. A is a rational number, which means it has a multiplicative inverse that's also rational. And so A inverse is actually the number that we want. So we can assume that b is not equal to 0, not because it has to be non-zero, but because if it is 0, then the answer is already answered. The question's already answered. All right, so now we're going to look for some c plus d alpha, which is going to be kind of our close to our multiplicative inverse, where we multiply it by a plus b alpha to get not 1, although that would be nice, but to get a rational number. Well, what's that going to be? That's going to involve some foiling. So we get a times c, a times d alpha, right? We get b alpha times c, which gives us bc alpha. And then we get b alpha times d alpha, which is bd alpha squared. Now, we'd like to write that in a way so that it looks like an element in Q of alpha, right? Because all the elements in Q of alpha are rational number plus rational number times alpha, but we have that silly little alpha squared that's kind of messing us up. But as you would see if you did the subring test on it, we can actually get that alpha squared into lower exponents by using the fact, remember, that alpha squared equals alpha minus 1. Remember, alpha was a root of alpha squared minus alpha plus 1, which means that alpha squared is equal to alpha minus 1. So we can plug that in for alpha squared, and then we can multiply everything out, collect like terms. That is something that you don't need to see, but when you do all that work, this is what you're going to get. You're going to get AC minus BD plus AD plus BC plus BD times alpha. All right, so remember, we want that to be rational. And if you look at that expression, the thing that's going to make it rational is if we can somehow make that alpha part disappear, right? The alpha is not real. But if that alpha part could disappear, we'd just be left with AC minus BD. That is rational, and that's exactly what we want. So the easiest way to do that is to let AD plus BC plus BD equal 0, the coefficient of alpha. Because if that coefficient is equal to 0, multiply that 0 times alpha, poof, the alpha disappears. Now remember, we get to choose our C and D to be whatever we want as long as it makes AD plus BC plus BD equals 0. Now we might have more than one choice, we might not. But it might help to solve for one of the things in there, either for C or for D, and to see if that gives us any insights. And either one can work, but I'm going to go ahead and solve for C, right? Because C is one of the things that we want to figure out what it is, and maybe solving for C will help us do that. One nice thing that happens when we solve for C is that, remember, B is non-zero. At least we're assuming B is non-zero for this part of it. So when we solve for C, we can divide both sides by B. The B being in the denominator is not going to hurt us because it's non-zero. So we end up with negative AD minus BD all over B. The other nice thing about that expression is if you look at the numerator, both of those terms have a common factor of D, right? So I can factor out that D from that expression up top. And actually, I'm not just going to factor out the D. I'm going to factor out a negative D so that the other factor doesn't have any negative signs in it. So we get negative D times A plus B on top and then B on the bottom. And so now that helps me, if I'm looking at that, remember, I have choice over what I want C and D to be. The only thing that's demanded me of those choices is that when I choose C and D, I should have C equal to negative D times A plus B all over B. And maybe a nice choice for D would be something that canceled out that B in the denominator, something that made it so that I didn't have to deal with fractions. And so I'm going to choose, well, you could choose just B if you wanted to, but since I don't like having negatives up there either, I'm going to choose D equal to negative B. And when you do that, not only does the B cancel out, but the negative sign cancels out as well. And so you end up with C equal to A plus B. So I know what A and B are. Those are given. A plus B alpha was the thing that I wanted to find the multiplicative inverse of. And so I'm going to choose D to be negative B, C to be A plus B, and that is going to give me, well, not my multiplicative inverse, but something very close. So now if I multiply out A plus B alpha times C plus D alpha, remember, we chose C and D so that alpha part disappears, right? That AD plus BC plus BD times alpha disappears. So all we're left with is AC minus BD, just the rational part. Then we can plug in D equals negative B, C equals A plus B. That gives us A squared plus AB plus B squared. And then we're going to use this to find the multiplicative inverse for A plus B alpha. So we have A plus B alpha times C plus D alpha equal to A squared plus AB plus B squared. If we divide both sides by A squared plus AB plus B squared, first thing we have to do is put in C equals A plus B and D equals negative B, right? That'd be an appropriate thing. So we get C plus D alpha equal to A plus B plus negative B times alpha. So that means if we want to find the multiplicative inverse, now we're going to divide by A squared plus AB plus B squared. And then we end up with A plus B over A squared plus AB plus B squared plus negative B over A squared plus AB plus B squared times alpha. And notice that both of those nasty looking fractions are rational numbers. And so we have a rational number plus another rational number times alpha. That's in Q of alpha, which means that A plus B alpha has a multiplicative inverse in Q of alpha. So what you're going to do in the next set of in-class activities is do the exact same thing, but in its most generality. So now what you're going to do is find we're going to have a root of alpha squared plus B alpha plus C, where B and C can literally be any rational numbers. And then prove that Q of alpha is indeed a field. All right, so the PDF where this problem is called General Field Extensions, and it's on the PDF file included with this video.